So I have chosen this topic because when our time, early 90s, when we were doing research, hardly there is any computational facility. So mostly physics people were involved in the structure elucidation. Nowadays, it is the journal requirement, you can say, every chemistry lab, whatever compound you are synthesizing, you have to supplement it with the crystal structure. Unless you do the crystal structure solution, it is not possible to publish your work and authenticate the things. So very basic requirement for a chemist is nowadays is to supplement their finding with the crystal structure. So it is the basic requirement of every lab. So what happens now? Whosoever is doing this research, because now lot of machines are there in almost every very good lab, you can say. When we were doing research, hardly any diffractometer, I think 5 to 6 diffractometers in whole the country. So we have to keep in line and we get a time of a week or so in every lab. So in a year, hardly we get 5, 6 samples. If 1 or 2 sample is already reported, our 50% work goes waste in that time. So what we were doing, we were manually plotting the RTAP because it is not possible to plot the temperature parameters. So whenever we do structure solution in our time, we get a set of coordinates. Then we take a graph paper, we plot it on the graph paper and do the molecular plotting. Similarly, in Pecky diagram also, we do the manual plotting. So I have published papers in our time, PhD work in acta crystallographica C by manual plotting because we don't have plotters. Printers now, you give your command, you get all the diagrams in 1 minute, I think nowadays. In the morning, you synthesize the compound, you put it in the diffractometer. By night, you are able to get the structure. And within a day or two, you are able to send it to a very good journal. But in our time, it takes lot of time to make the things because we don't have printers at that time. We have to do plotting, and for plotter also, you need plotter pens, which a common research scholar cannot afford at that time. So all the research work we at that time, early 90s, we were doing manually. And at that time, we learned the things. But nowadays, everything is done by machines. So my advice to the younger students who have taken this chemistry are, because nowadays very few people from physics background, they are doing structure solution, mostly chemistry people are involved. So you should have some basic knowledge about how we are finding the structures. One should not depend on the machines only. That's why I have chosen this topic. Because if you are solving 10 structures, you will get problem of disorder in almost 3 or 4 structures. Once you get a problem of disorder, if you don't have the basic knowledge of crystallography, you are unable to send it for publication. Basic requirement is now check safe. Unless you remove all the A level alert, B level alert, so it is very, very difficult to publish the things. It's okay, machine is doing its part. We are getting help from the machines, but alongside the machines, you should have basic knowledge how to solve the disorder. Nowadays, hardly any week passes, I get structures of solution for disorder solution from one part of the country to another part of the country. Because students who are doing this kind of work, they don't go the basic. Because it is not difficult to solve the disorder. Lot of programs are now there, which takes care of twinning, etc. But if it is a substitutional disorder, static disorder, first of all, one should be able to find out what kind of disorder it is. Whether it is dynamic disorder, it is substitutional disorder, it is static disorder. So unless you have the basic knowledge of this, twinning is taken care by the program itself. I think if there are crystallographers sitting here who are doing crystallography, this kind of work, they are able to solve the twinning problem. What when the disorder of substitutional kind comes, or whole molecule is disorder, then it is very, very difficult. Sometimes it takes months to solve a single disorder. That's why I have chosen this topic this time to say this. So this is what the power of programs and computer has made remarkable progress in the same period. There has remained one domain where crystallographers still spend a lot of their time, and this is when the structure under investigation is disordered. The very first hint you can get from the displacement parameters. So whenever you solve any structure, you get a set of coordinates, x, y, z, and then the displaced parameters. So equivalent isotropic temperature factor gives you a very first-hand information that the structure you are solving, whether it is disordered or not. Why disorder? Why disorder? From where disorder comes? Every unit cell has exactly the same orientation with all molecules in the same conformation. This is the basic definition of a crystal. All unit cell has the same environment. Only then we call a molecule crystallizing in a single crystal form. However, an ideal crystal does not exist. And in most real crystals, there are several lattice defects, and are impurities. So it is very, very difficult to get an ideal crystal. Whatever crystal you are growing, you have some kind of disorder present in it. Frequently, parts of molecule, it is not that, it is very, very rare that whole molecule is disordered. If a whole molecule is disordered, then there is some kind of problem in the data collection or something is going wrong. But part of the molecule, in some extreme cases, whole molecules are found in more than one crystallographic independent orientations. Sometimes when we talk of liquid crystals, they are very, say, rod-shaped molecules I am able to crystallize a liquid crystalline material in rod-shaped molecule. The length of the molecule is such that it is very, very difficult to have symmetric molecules in the unit cell. What we get independent molecules. But one can distinguish 4 cases, more than one molecule per a symmetric unit. They are those molecules which are not sitting by any kind of symmetry. If there are 4 molecules in a unit cell, all the 4 are independent, then you have to solve each molecule differently. If they are related with some kind of symmetry, then you are only bothered with one molecule only. Then twinning is nowadays, earlier it is not, but nowadays very powerful programs are there. Twinning is taken care. In shellac itself, twinning is taken care. Then comes disorder, part of the molecule. Mostly central part of the molecule is not disordered. It is the side peripheral parts, the substituents, but whatever we have attached in the molecule, they show disorder. It is, although it is there central, sometimes central part of the molecule also, because of its rigidity, does not show any disorder, but some molecules show disorder. Or whole molecular disorder. Whole molecule disorder is very, very less. Now, this is the basic. From here, whenever you collect data, you solve the structure, and then simultaneously you plot it. So if your one terminal molecule is showing this thermal ellipsoid like this, so you can immediately say there is a disorder in the molecule. Then you have to resolve it, otherwise it will give error. In check safe, A level alert will come. Isotropic temperature factor is very, very high. It is not matching with the adjacent thermal ellipsoid. Now you can say anisotropic displaced parameters of a disorder. This is the ethyl group. On the left without and on the right with the disorder. We have solved the disorder here. We have bifurcated this part of the atom into 2 parts here. So now it will not show any disorder. If we have occupancy 1, it may be 70-30, it may be 50-50, depending upon how much disorder is present. If it is 5 to 10%, you can ignore it. If it is more than 20%, 30%, then you have to solve it and then refine it. If the disorder is ignored, the refinement program tries to describe both atom positions with one ellipsoid. If you try to ignore it, so both the positions, molecule is spending some time here, sometime here. It is vibrating. It may be orientation depending upon different orientations in different unit cells. So giving rise to here, if the disorder is ignored, the refinement program tries to describe both atom positions with one ellipsoid, you can see from here, giving rise to a cigar-shaped probability ellipsoid. It is not an ellipse, it is a cigar shape. So this is the first-hand information from the R-type diagram itself that your structure is showing some kind of disorder. Three major classes of disorder are dynamic disorder, static disorder, substitutional disorder. Both dynamic disorder anyway we can solve by taking the nowadays almost every diffractometer has low temperature facility. You collect data at low temperature, dynamic disorder is taken care because vibrations will be very, very less and your disorder component will not show more than 5% disorder. But if it is static or substitutional disorder are mostly static kind of things. If the disorder is static, if you collect the data even at low temperature, so you are not able to resolve its disorder component. Both dynamic and static disorders are treated in the same way during refinement. Dynamical disorder is even frozen at low temperature, whereas static disorder persists even at low temperature. By collecting data at low temperature, there is no effect on substitutional or static disorder. Substitutional disorder describes a situation in which the same site in the two unit cells is occupied by different types of atoms. Suppose I have a substitution of a phenyl ring where it is chlorine attached to the phenyl ring. Suppose this is the chlorine atom. In one unit cell, it is freely moving substituent phenyl ring. In one phenyl ring, in one unit cell, it is sitting like this, other unit cell, it is like this. So in that case, it is a substitutional disorder. Chlorine is coming 50% occupancy at the right side, 50% occupancy at the left side. So that we call it as static disorder or substitutional disorder. A situation in which the same site in the two unit cell is occupied different types of atoms. This type of disorder that can be observed mostly with inorganic materials like minerals. So in order to cope well with this type of disorder, accurate knowledge of composition is very, very important. Because then thermal, if you don't have the substituent is chlorine or some other sulfur, so you should have some basic idea. Even from the shape of the ellipsoid, we can make out whether it is a low atomic number atom, you are giving high atomic number atom. If you are making carbon oxygen or oxygen carbon, ellipsoid will be very, very small or very, very large. So from the shape of the ellipsoid itself, you can make out whether you are assigning the composition to the molecule is correct or not correct. So that's why some basic knowledge to the crystallography is very, very important. Unless you know that if atomic number is less, what kind of ellipsoid we will get. If atomic number is more, what kind of ellipse we will get. So you are unable to resolve it. So we will take a very simple example here. Here you can see we are shining X-rays on the crystal. So crystal is a large number of unit cells, this side, downside, everywhere. That's why we call it as crystal. Suppose in the one unit cell, your molecule is like this. In the second unit cell, it is slightly rotating this substituent. Say it is OCH3. Methoxy group is there. In this case, it is slightly rotating like this. Fourth one, it is like this. There are a number of unit cells. Slightly orientation change of 5 degree or 2 degree or 1 degree is there. So when you crystallize the molecule, you will get information. You are plotting it. You are plotting a single unit cell. You are not plotting a whole number of unit cells. So in that case, then it will be a combination of all the orientations. Now you can see your coordinate has to be here X, Y, Z. Now your coordinate distributed in the whole space here. Your now ellipsoid will be from this place to this place. Because in first unit cell, say methyl group is here, second unit cell methyl group is here, third unit cell methyl group is here, fourth unit cell group is there. So you will get a ellipsoid like this, not the point ellipsoid. So if now this ring is stationary, it is not moving. In the first unit cell is your ring is this, second is also this, third also this. If in the first unit cell your phenyl ring say is like this, second unit cell it is rotating like this, third it is rotating like this, fourth it is rotating like this, then your whole molecule is disordered. Not only single atom, all the atoms in the unit cell will be disordered, they will show disorder. Then we can say your whole molecule, complete molecule is showing disorder. This is a very general basic definition of disorder. Why disorder? Because your this substituent is slightly rotating in the one unit cell to second unit cell to the third unit cell. Now, the refinement program has number of constants. Those students who are doing crystallography, they are no number of constants and restraints are present. You can, for temperature, EDAP command you can give. Like this part command is there. It refines disorder by dividing the disordered atoms into groups. So whatever we got, normally we divide it into two groups. Even then, if there is disorder, we take the example of, in the coming slides, CF3 group, which is rotational disorder. It is very, very common. Wherever in the structure CF3 is present, it will always show disorder. So the occupancy of disordered groups are allowed to refine. We cannot keep the fixed occupancy. If you will keep the occupancy, because normally in the refinement, we keep the occupancy as 1. So whenever we have to solve the disorder, we have to keep this occupancy as free. We have to allow it to refine. Maybe it is 70%, 30%, 20%, 80%. Unless you allow it to refine, your program will not run. As disorder is not expected at the early stages, it is in the final stage you come to know that your structure is disordered. Disorder in a later refinement cycle has to be inferred from the magnitude of equivalent isotropic temperature factor. So equivalent isotropic temperature factor is all the temperature factors, then there is a program. In our time, we were doing it manually. Nowadays, the program itself takes care of the equivalent isotropic temperature factor and it plots as a thermal ellipsoid. In crystal, the shape and size of thermal ellipsoids is one of the most important indicators for problems with molecular model. So what kind of disorder is present? A very small ellipsoid indicates that the corresponding atom may be in fact be heavier than the one currently contained in the model. Suppose we have refined oxygen as carbon, your ellipsoid will become very, very small. So from there, you will see in the ring that 5 atoms, they are showing same almost size ellipsoid. One is very, very small. So you immediately come to know, if you have studied all this disorder, that you have put oxygen as carbon and vice versa. If it is carbon, you are giving it oxygen, yet then the size of the ellipsoid will increase. Elongated cigar-shaped ellipsoids are another sign indicating disorder. Flat, other shaped molecules, either they show pseudosymmetry or incorrect space group. Suppose your space group is P21YA. You are giving it P21YC. Hardly there is a difference of 1/4 along one of the axis, motion of the molecule. So you should have clearly knowledge whether the space group is P21YA, P21YC. Otherwise, from symmetry point of view, very, very small difference. When you plot the equivalent diagram of a space group, hardly you will notice any change. But when you refine it, P21YN as P21YA, then all these problems will come. Now, suppose this, I have taken it as one of the example. Firstly, when I solve the structure, only these two, this is the terminal chain and hexyl chain. Say it is a liquid crystalline material. So only these two atoms, they were showing the disorder. Only 2 terminal atoms were showing disorder. All other atoms, they have the same, almost the same thermal ellipsoids. When I have resolved these two by bifurcating into 4 parts, 1, 2, 3, 4, then now you can see C104 is not showing disorder. Only C105 and C106 were showing disorder. Their shape is such that they are showing disorder. Cigar shaped. Now when I resolved these 2 atoms in the molecule C06, C06A, so now C104 started showing elongated shape. So now this means that this is also disorder. Now I have resolved it. I have bifurcated into two parts. Now the disorder now has gone from C104. Now you can see C103 is not that much elongated, but still it is showing some kind of small disorder. Maybe it is 50%, it may be 30%, no, it may be 20%. We have to resolve this also. We have resolved this. Now you can see C102, it is almost showing nil disorder. Even disorder of 5% we can ignore. So you have to do systematically the refinement. It is not that only two atoms are showing disorder. You will resolve them and leave it. Then the next you have to see whether what is the temperature factor. Then you have to resolve this. After that you have to see the earlier one. So now you can see the NXL chain. We have removed the disorder from 1, 2, 3, 4, 5 atoms. We have bifurcated 5 atoms of the chain into 10 atoms with occupancy maybe 60, 40, 1 is 50, 50, 1 is 30, 70, like this. This is how disorder is resolved in the long chains. Now I will come to the example I have shown earlier. If here I have put chlorine, in other case, because now this one, it will rotate from unit cell to unit cell. In one unit cell, the molecule, this 5-membered ring, sulfur molecule, sulfur atom is sitting like here. In the very next, it is showing at this place. Because phenyl ring, it is free to move. It will move like this. Now, whenever you will solve the structure, you will find here disorder in this molecule as well as this molecule. Now, this atom is 50% carbon, 50% sulfur. This atom is 50% carbon, 50% sulfur. Earlier it is one occupancy of carbon, one occupancy of sulfur. But both the atoms, they are showing disorder. So this is static disorder, or you can say it is a substitutional disorder. Okay, sir. Disorder thiophene ring as seen after refinement and a disorder model with the original position. Bonding axis is rotating by 180 degree. So mostly when phenyl rings are here in this also same ring. Here there is no problem. There is also situations like this. But here disorder is very, very small, 5%. When we solve this molecule is showing disorder of 5%. This molecule is showing disorder of 50%. So you can see, even though a sulfur atom takes the place of a carbon atom and vice versa, carbon is taking the place of sulfur in the other unit cell. Because unit cell is a large number of unit cells in one direction, in other direction. So the result of crystallization process, the different orientation of thiophene ring are a result of the crystallization process and would therefore be rather classified as a static than a substitutional disorder. Now solvent disorder, you have seen that mostly DMSO, whenever you crystallize your molecule in DMSO, 90% DMSO will come as a disorder. Or some water molecules in protein crystallography, those who are doing crystallography in proteins or in large molecules, macromolecules, water molecule is showing disorder. Disorder structures can also be classified on the basis of what part of the structure is disorder. As a rule of thumb, it may be stated that smaller the molecule that we want to look at, the bigger the probability that it moves with the temperature. Small parts of the molecules, the side substituents, peripherals, thus disorder in solvent, because if molecule is bigger, water as a solvent is very, very small. So water will show the disorder, not the bigger molecule. Thus disorder in solvent molecules tend to be more frequent than disorder in bigger molecules. Sometimes bigger molecule as well as water solvent, they both show the disorder. This problem is of particular interest and importance in macromolecular crystallography and in protein crystallography, where water component is almost 40%. Now you can see here, this is very interesting molecule I have solved. It is a steroidal molecule I have taken. Two solvent molecules, because this is the acetic acid. When I have solved all the molecules of acetic acid, they were showing 50% occupancy, 0.5. This molecule is showing 100% occupancy. But one oxygen of acetic acid solvent, it is showing one occupancy. So it is very, very difficult to resolve it. It took me months to resolve this. So now what happened? This oxygen has one occupancy. All other atoms of the acetic molecules, they have 50% occupancy. Now it is not the oxygen of acetic acid, 50% occupancy of water solvent also present. So this oxygen is 50% belonging to the acetic acid, 50% belonging to the water solvent. Atom O28, this one, of CH3COOH acetic acid is further disordered into another position, O28 with the refinable occupancy. Further, this oxygen was showing disorder. We have resolved it. So in structure refinement, atom C26 has 100% occupancy while all other atoms. So unless you have the knowledge of crystallography, no one can solve this kind of disorder, where one atom of a particular solvent is showing 100 occupancy, other is showing 50% occupancy. Then you have to realize why it is coming so. So then the idea came, it may be a water, half water solvent. So then when we did, R factor drastically came down. Otherwise, your R factor will stuck up to 10%, 11%. You are unable to get 4, 5% disorder. Sir, hardly 2 minutes. So because this whole molecule is showing one occupancy, your solvent is showing 50% occupancy because it is sitting on the two-fold axis. 50% belonging to this unit cell, 50% belonging to the other unit cell. So two-fold rotation Smith is present in the acetic acid solvent only. Partial fragment disorder. Now, your whole molecule is stabilized 100% occupancy. But this acetoxy, 3 acetoxy substituent, one of the oxygen of 3 acetoxy is showing disorder. So we have bifurcated into 2 parts, O22 and O25. Looking at the magnitude of displaced parameters, it can be shown that U values tend to be smaller in the center of the molecules, but however, acetoxy group is showing large your thermal parameters. So this is the example of your whole molecule is showing disorder. But it may be, sometimes your data collection may not be correct, or there may be other reasons in that case. So CF3 molecule I have talked earlier. So wherever CF3 molecule is present, it always shows rotational disorder. So whenever you solve it, you will get 3 more peaks. Then you have to resolve fluorine into 2 components. Sometimes fluorine has to be resolved in 3 components. So disorder model over 2 positions here, same but fluorine atom. Here you can see it is complete circle. We have made refinement as isotropic. When you will make it anisotropic, it will become ellipse. So I will skip it because of time constraint. So this is another molecule. I am still working. So it is already reported in ACTA in the year 2007. This molecule here, they have reported it. So they have shown it as a substitutional disorder, this oxygen atom at this place as well as this place, because it has the same environment in this chain. In one unit cell, it is coming here, other unit cell, it is coming here. Same molecule when we have taken for structure solution, I am still working on that. So what all parameters are same, all unit cells are parameters are same. In my case, this ring is coming disorder. I have resolved the disorder of this 6-membered phenyl ring. So now in this case, in my case, it is not the substitutional disorder. Oxygen is not taking 50% occupancy or 50% occupancy. It is ketoenol form. It is here OH group, it is a keto group. 50% occupancy of the keto group, 50% occupancy of the enol group. Moreover, at this place, I am getting one more peak. When I solved it, it is coming as NH3. Still, I have not yet sent for publication. I am making it to be 100% sure that whatever it has crystallized. Now, in my case, this is one molecule as keto form crystallizing in one unit cell. In other unit cell, molecule is crystallizing as enol form.
Vivek, time ho gaya. Time.
Last slide, sir. This is. In the third unit cell, it is crystallizing with the NH3 group. So all the three molecules, they are crystallizing as one molecule. Sir, last. So this is, I have put in this structure number of restraints and constants you can see. So unless you do some kind of basic crystallography, you are unable to do this kind of constant and restraints in the modeling of the molecule. So my advice to the younger generation is, for resolving disorder in molecules, basic chemical knowledge and understanding of the fundamentals of crystallography is very, very important. To the answer to the question of whether a specific disorder is worth refining as much based on experience as the assessment of data quality and difference diagnostic maps. Thank you.